Welcome to Student, a series of animated calculus videos that will help you prepare for the AP exam. These videos were made by students for students.
Hi, welcome to a short explanation of revolving solids around other axes. When revolving about another axis, in this case we'll be looking at the line y equals 2, regardless of where your axis is, your radius is always going to be the distance between your function and the axis of revolution. The distance is the radius of all the circles that you are adding up. Distance between two functions can be found using subtraction. If we look at the function y equals x squared, and we want to revolve it around y equals 2 between x equals 0 and x equals root 2, our radius used in our integral would be 2 minus x squared, because this is the distance between the two curves. Our limits on our integral would be 0 and the square root of 2, so we are revolving the area in blue around the red line. We always do top minus bottom when finding our radius, so in this case the top will be y equals 2. Then you just plug that radius in and integrate. Washers are just a little bit different from discs because they have two pieces rather than just one. Just like washers around the x-axis, you revolve the curve that is further away from the axis and find that volume, and then subtract the volume obtained by revolving the inner curve. In the graph above, we are going to look at revolving the area between y equals x squared and y equals x around the line y equals 2. Y equals 2 is in red. So first you would revolve y equals x squared around y equals 2 because it is the outer function. It is further from y equals 2. Like we saw with discs, when we revolve around a line that isn't the x or y axis, we use the distance between the function and the line as our radius. So our radius for the first revolution is 2 minus x squared. And then we would just plug it into our formula and integrate to get that volume where the area is revolved. Next, we are going to subtract the volume of the inside function to actually get our washer, which in this case would be the volume from rotating y equals x around the line y equals 2. We do not want that volume included. When revolving y equals x, the radius would again be the distance between the function and our axis of revolution. So our radius in this case would be 2 minus x. Then once again we would plug in and integrate. The integrals can be combined into one or they can be left split up. It is completely up to you. When we subtract the inner volume, or the thing that is highlighted in green, we are left with the area that is in red. And this is our washer. This is the thing that we are essentially revolving around the axis y equals 2, and the volume we are finding is the volume obtained by revolving the area in red. I hope this little lesson helped. Now that you've learned the basics of revolving solids, we're going to work through two past AP FRQs to get some practice. The first FRQ is a question number 1 from the 2003 test. The question is, let R be the shaded region bounded by the graphs of y equals the square root of x and y equals e to the negative 3x, and the vertical line x equals 1 as shown in the figure above. Find the volume of the solid generated when R is revolved about the horizontal line y equals 1. To start, we know that y equals the square root of x is the top line, y equals e to the negative 3x is the bottom line, and x equals 1 is the vertical line on the right. If you look more closely, they're asking us to revolve R around the horizontal line y equals 1, so we're going to draw in the line y equals 1. Now, we know that the rightmost bound of the region R is the line x equals 1, but we haven't found the left bound yet. So to find the left bound, we're going to need the intersection between y equals the square root of x and y equals e to the negative 3x. This is a calculator active problem, so you can start by graphing the two curves on your calculator and using second trace to find their intersection. Then if you return to the normal mode of your calculator, you can recall the x-coordinate of their intersection. It can be helpful to store this number in one of the variables in your calculator so you can use it later without having to round or type out the whole long decimal. So now, we know that the two lines intersect at 0.238 and 0.489. So now we have both the left and the right bounds of the region R. Next, we're going to actually revolve R around the line y equals 1. If we look at the general formula for the volume of a revolved solid, we see that it's pi times the integral from a to b of big R squared minus little r squared. Big R is always the distance from the axis to the outer edge of the region we're rotating. So if we draw a representative rectangle from the axis to the outer edge of the region, we see that in this case, our big R is 1 minus e to the negative 3x, because 1 is our axis and e to the negative 3x is our outer edge. We always do top minus bottom, and our axis is on the top and our outer edge is on the bottom. Then little r is the distance from the axis to the inner edge of the region we're rotating. If we draw a representative rectangle from the axis to the inner edge, we see that our little r is 1 minus the square root of x, because our axis, 1, is on the top, and our inner edge, the square root of x, is on the bottom. Then if we plug all of this back into the formula, we get that the volume is pi times the integral from 0.238 to 1 of 1 minus e to the negative 3x squared minus 1 minus the square root of x squared. We get our limits for integration from the bounds for the region R. The left bound is the intersection between the square root of x and e to the negative 3x, which is 0.238. Because it's our left bound, it's our bottom limit of integration. Our top limit of integration comes from the rightmost bound of the region R, which is the line x equals 1. If we go back to our calculator, we can just plug the whole integral right in. Remember that we stored the x-coordinate of the intersection in the variable a, so we can just use the variable a as our bottom limit of integration so we don't have a rounding error. Then your answer is a long decimal, but on the AP test we always round to 3 decimal places. So we're going to round that value to 1.424, and that's our final answer. Then if we look at the scoring guidelines, we see that this part of the question was worth 3 points. You would get 2 points for the correct integrand and 1 point for having the correct answer.
Hey everyone, so today we're going to be going over FRQ number 5 from 2019. So as you can see, the prompt says, let R be the region enclosed by the graphs of g of x equals negative 2 plus 3 cosine of pi halves x, and h of x equals 6 minus 2 times the quantity x minus 1 squared, the y-axis, and the vertical line x equals 2 as shown in the figure below in this case. We're going to be looking at part C, which asks us to write but not evaluate an integral expression that gives the volume of the solid generated when R is rotated about the horizontal line y equals 6. Now, that's a lot to look at, so I pulled out the important stuff. We have g of x, which in this case is our bottom function. H of x is our top function in red. Y equals 6 is the axis that we're going to be rotating around, and we're between x equals 0 and x equals 2. For this problem, you know we're going to be using washers because the area doesn't line up completely with the axis that we're rotating around. So for the general form of finding the volume with washers, it's pi times the integral from a to b of big R squared minus little r squared dx. Let's start with the easy part, finding the limits. As you can see, the problem says that we're between x equals 0 and x equals 2. So a equals 0 and b equals 2. Now for our big R, you do your axis minus your outer function in this case because the axis is above our function. So big R equals 6 minus g of x. And then for the little r, you do the axis minus the inner function, and that'll get you the little bit of volume that's not being, or that we have to subtract out to find the volume when we rotate around the axis. So little r is 6 minus h of x. And then you can just put that all together for a final answer of pi times the integral from 0 to 2 of the quantity 6 minus g of x squared minus the quantity 6 minus h of x squared. Now let's go over the scoring guidelines. So again, here's our answer. And as you can see, the first point comes from having the limits and the constant, which we clearly have. That's the pi and the from 0 to 2. And since it says and, you have to have both of those in order to get the point. So if you forgot the pi, you wouldn't get that point. Or if you have the wrong limits, you wouldn't get that point. But we have it, so yay. Now, the second point is for the form of the integrand, which basically means that you need to have some big R squared minus some little r squared, even if it's not the correct big R and little r. And then the final point is for the integrand, which means that you have the correct big R and little r and everything is right. The one exception is if you forgot the pi, you probably could get the third point, simply because you would have lost a point for the first point, and usually College Board doesn't try to knock you twice for a stupid little mistake. I hope this helps.